Let's solve Unit 8 Theory of Computation and Compilers questions. Let L is equal to AB, AA, BAA. Which of the following strings are not in L? If you find these three patterns in the strings given in the options, it means the strings are in L. But the question is, they are asking which string is not in L. It means we know from the four options only one string is not in L. L star is L closure. It's a combo of all the patterns inside the language that you can find in these options. So let's start with 1. A B A A B triple A B A A. So AB is there, then AA is there, then we have BAA, so it is there. Again we have AB and AA. All patterns are present in the string, so this is in L. Second one, we have 4 A's, single B and 4 A's. So let's take AA, then we have BAA, then AA. So second one is also present in L. Third one, we have single B, 5 numbers of A, single B, 4 numbers of A, and then another B. So BAA, then we have AA, then AB, again we have AA, then we have AA, and we have B left out here. So even if you want to take this to be AB, then this A will be left out. 3 is not in L. Let's check the fourth one. We have B, 5 numbers of A's and BAA. So we have BAA, then we have AA, then AB, then AA. So this is also in L. So the only option that is not present in L will be option number 3. Option 3 will be the right answer. Next question. Let A is equal to A comma B and L is equal to A star. Let X is equal to A parent, B parent, where N is greater than 0. The languages L union X and X are respectively. Basically, let's take X. X is equal to A power N, B power N. So, if you take A power N, B power N format, generally they say this belongs to CFL. The reason is when you take a push down automata, just imagine a stack. The number of A's will be equal to number of B's as per this language. They say N is equal to a value greater than 0. So it can be N is equal to 1, N is equal to 2, N is equal to 3, etc. So if it is N is equal to 1, it is AB. If N is equal to 2, it is AABB. If N is equal to 3, it is triple A and triple B. Generally, if you take a stack, the number of A's will be pushed onto the stack, and whenever a B is encountered, A will be popped out. This will tell whether A's count is equal to B's count. So A power n, B power n is always a part of CFL. Now we have to check whether X is regular or not. Just take the pumping lemma. Let L be a regular language over some alphabet. There exists a positive integer, the pumping length of L, such that for every string of at least length P, there exist strings X, Y and Z that belongs to the alphabet such that S is equal to X, Y, Z. So they have given three conditions. Let's take N is equal to 3 triple B string as of now. Now we have to choose X, Y, Z from this string. So let's take A, B to be X and Y together. So what is X? X is this single A and let Y be AB. So here Y should not be equivalent to epsilon. It means Y should not be empty. Either you can make this to be X, this to be Y, or out of B, you can make this to be X and this to be Y. So we can try for both the cases. So we have the length of X and Y together, that is less than or equal to P. Here we will make a 3 length string, so it is less than or equal to 3. This condition is satisfied in both the cases. So this is case 1 and this is case 2. Next, Y is not equal to epsilon. Yes, Y is existing. Next we have to check for X, Y power I, Z, where I is greater than or equal to 0. For I is equal to 0, here x is equal to a and y is equal to ab. So if we have y power 0, ab should not exist. Then what will happen to the first string? We will have a, this ab will be absent, then we will have bb. If we have I is equal to 1, then we will have triple A and triple B, fine. When we go for I is equal to 2, A will be present and AB together will be present as AB, then BB. Is this string present in the language X? This does not belong to it. So from this we can conclude that X is not regular. So now let's check this. We have X is equal to AA. When we say y power 0, it means we are removing 1b alone. This will result in triple A double E, which is not a part of X again. So the count of A's should be equivalent to count of B's. You can choose any X and any Y with a maximum length of 3 because we have chosen that P to be 3. But the thing is, when you compute this for a set of iterations, the strings after the computation should be present in the language set. This X is not regular. So they are asking L union X and X respectively. So this X is the second part of the option. So whichever option is having not regular will stay. Whatever has regular in the second option will be ruled out. Now we have to find L. So L is equal to A star. What is A star? A star is, you can either have 0 or more occurrences. So we can have epsilon, we can have A, we can have B, we can have AB, we can have any combo. It is having the expression A star, definitely L is regular. So L is regular and X is not regular. So what about the union? L union X. What kind of strings it will have? It will have epsilon A, B. Then it will have double A, double B, triple A, triple B. When you have a union operation, all the strings of A power n, B power n will be sitting inside this L union X. Let's take L intersection X. This is not equivalent to 5 because L contains all the strings that X has. So this is not equivalent to null because A star has all strings of X. The intersection cannot be null. So let's check for pumping lemma of L union X. Whichever string we rejected in X, we'll just take. These strings were rejected by X. But just check for L union X. A star has all strings of X along with its own strings. This is a possible combination in A star. So this is right. This is a possible combination in A star. So it is there. When you apply the pumping lemma rule for L union X, all the strings are present in L union X. So this makes L union X to be regular. So not regular is rejected here. Option 3. L union X is regular but X is not regular will be the right answer. So generally if L is regular and X is regular, we need not even check this. We can say L union X is also regular. But in our case, one is regular and another is not regular. So in that case, all these strings given by X are acceptable in A star. Keeping that in mind, we mark the union of L and X to be regular. So we have an additional statement here. If a language L1 is regular and if language L2 is not regular, we have to check if language 1 intersection language 2 is equal to null. If the intersection gives a result of null, then L1 union L2 will be not regular. In case if L1 intersection L2 is not equal to null, then L1 union L2 will be regular. It means both have some common elements. Keeping this point in mind, we checked for L intersection X. Next question. Which of the following symbol table implementation is best suited if access time is to be minimum? So what is a symbol table? It's an important data structure created and maintained by the compiler in order to keep track of semantics of variables. It stores information about scope and binding information about names, information about instances of various entities such as variable, function names, classes, objects, etc. So this is a data structure and they are asking which implementation is best suited if the access, that is the search time, is to be minimum. So linear list takes O of n for both insertion as well as search. And next is search tree. You can take for binary search tree. Complexity will be O of log n. It's for both insertion as well as for search, because you're going to divide the content into two and then you're going to work with only one half. So it is log n. What about hash table? The elements are stored in an array with index numbers. So when you want to search, you will exactly locate it. And when you want to insert, you will calculate the slot based on a particular hash function and immediately insert it. This means that it takes O of 1 time for insertion as well as for searching. Now we have a term called self-organization list. What it is? It is a list that reorders its elements based on some self-organizing heuristic to improve average access time. This particular part states that the access time is actually more and the reordering is done to improve the average access time. It is O of 1 for insertion, but for search it takes O of n. So we have to consider the access time, though it takes only O of 1 for insertion, but it is O of n for search. So these two will get ruled out here, and because of search time here, fourth one will also get ruled out here. Option number 3, hash table, will be the right answer. Hash table implementation is best suited if access time has to be minimum. Next question. Consider a grammar E produces E plus N, E into N, then it has N. For a sentence, N plus N into N. The handles in the right-sentential form of the reduction are: bottom-up parsing is the process of reducing a string to the start symbol of the grammar. In top-down parsing, what they will do is, from a start symbol, then this E will get expanded to E plus N, then into N, then this E will get converted to N, this plus N, and this into N. So this is top down. What is bottom up? Going from bottom to the top is bottom up parsing. We are reducing a string. So this is a string to the start symbol of the grammar. At each reduction step, a specific substring matching the body of a production is replaced by the non-terminal at the head of that production. So here the body of the production will be this one or this one. It is replaced by the non-terminal at the head of the production. Here this is the non-terminal for the production. Let's take the string n plus n into n. So this n will be replaced by a non-terminal e and the rest will stay. Then e plus n will be replaced by the non-terminal and the rest will stay. Now the complete production is replaced by the non-terminal e. So this is how we start from the string and come to the start symbol of the grammar. So this is what they say, the production gets replaced by the non-terminal at the head of that production. So what is the question about is the handles in the right-sentential form of the reduction. So what are handles? Handle is a substring that matches the body of a production. So which part you are going to replace, that part is called the handle, whose reduction represents one step along the reverse of a rightmost derivation. Then what is a right-sentential form? A right-sentential form is a sentential form that occurs in the rightmost derivation of some sentence. When you get through the working of this particular problem, you will understand it better. Let's have the right-sentential form here and the handle that is going to be matching the body of the production, and the reducing production will be given in the third column. So let's start with the complete sentence given here. So this is what is given in the question, n plus n into n. The first handle that we are going to replace it with the production will be the first n. It is going to get replaced as e. So what is the production that helps us to do is e derives n or e produces n. This production is going to do that. Now after reducing the production, what happens in the right sentential form? This turns as e plus n into n. Whatever we did here, we are just placing it in three different columns along with the appropriate names. Only then you will be able to answer the question. What is the next handle we are going to work with? It is e plus n. So the handle that we work next is e plus n. And what is the reducing production? It is e derives e plus n. So what will the complete substring be replaced by? E. Now the remaining is into n. Now the handle will be E into N. What is the reducing production? E derives E into N. So which production is responsible for reducing this is given in this column. What is getting replaced is given in this column. And the right sentential form is the actual sentence that is given along with the replacement in the subsequent rows. So first we are changing n, that is the first handle. Then we are changing e plus n, that is the second handle. Then we are working with e into n, that is the third handle. So the handles in the right sentential form of the reduction are n, e plus n and e into n. Option number 4 will be the right answer. So you can ask me one thing. This is also right, but this is not the handle. All these are not handle. This is the exact sentence and this is wrong. This is a part of the right sentential form, but this is not a part of right sentential form. Option 1, 2, 3 are ruled out. Option 4 will be right. Next question. One of the purposes of using intermediate code in compilers is to. The analysis phase of a compiler breaks up a source program into constituent pieces and produces an internal representation for it called intermediate code. So you will have analysis phase here, then you will have intermediate code, then you will get into the synthesis phase. The synthesis phase translates the intermediate code into the target program. Front end of a compiler constructs an intermediate representation of the source program from which the backend generates the target program. So they have mentioned the front end and back end here and where the intermediate code is existing. The mission independent code optimization phase attempts to improve the intermediate code so that better target code will result. So from here what happens is what this point is telling. The code generator takes as input an intermediate representation of the source program and maps it to the target language. So let's check the options. Make parsing and semantic analysis simpler. So intermediate code comes after analysis phase, so this is wrong. Improve error recovery and error reporting, it has nothing to do with errors. Then the fourth one, improve the register allocation, it has nothing to do with it. The third one, increase the chances of reusing the mission independent code optimizer in other compilers. So here this term means it is attempting to improve the intermediate code so that better target code will result. Option number 3 will be the right answer. We'll say lexical analysis, syntax analysis, then semantic analysis, then we get into intermediate code. All these 3 steps together is what we call as analysis phase. So that's why parsing is a part of syntax analysis and semantic analysis. They don't have work with the intermediate code. Only after the analysis phase, intermediate code is produced. Next question. The sum of minimum and maximum number of final states for a deterministic finite automata DFA having P state is equal to. So let's take the tuple of DFA. Q is the set of states. The count is given as P here. Then we have the input symbols, then we have the transition function, then we have Q naught as its start state, and F is a set of accepting states. They say F is a subset of Q. It means all the states can turn as accepting states, or at least one state will be taken as the accept state. So from this we can say the start state or the initial state. This will be only one. The minimum as well as the maximum will be 1. What about the final state? Only when there is a finite state, the string will be accepted in a DFA. So minimum or at least one final state must be present. So at least in the sense it can be one or more than one. What about the maximum? I can use all the states to be the final states. So this all means the total number of states that is available in the DFA. Here they are saying there are P number of states. So the maximum will be P states. They are asking for the sum of minimum and maximum. What is the sum of minimum and maximum? Minimum is 1, maximum is P. So it should be either 1 plus P or P plus 1. Both are same. Option number 3 will be the right answer. Next question. 3 address codes can be represented in special structures known as. So from which part is this question taken? It is taken from the intermediate code. 3 address code takes its name from instructions of the form x is equal to y operator z with at most one operator per instruction. So operator is represented here. These are operands. Now let's see the various representations of 3 address codes. The first one is quadruples. So this is the 3 address code available and they have converted this into quadruples. Quadruples in the sense there will be 2 operand or arguments and 1 operator and the result. So quadruple means 4 things are involved. What is the next representation? It is the triples. So the representation of this expression is given in the form of triples. What are the things involved in triples? It is 2 arguments and an operator. The next one will be indirect triples representation of the 3 address code. So from this we can say there are 3 representations. One is quadruples, another is triples, and the third one is indirect triples. So C alone is not there. Patterns is not a part of 3 address code structure. Any option that involves C will be ruled out and the one that includes A, B and D will be option 2. Option 2 will be the right answer. Next question. Which of the statements are correct? Moore and Mealy missions. They are a part of finite state missions in theory of computation. Let's learn about them. Finite state transducers are associated with a read once only input file that contains a string from an input alphabet and an output mechanism that produces a string from an output alphabet in response to a given input. So this is the official definition. So usually in finite automata what happens is we have an input and we'll say whether it is accepted in a language or not. But in finite state transducers, there will be an input and there will be an output too. These Moore and Mealy missions come under finite state transducers. In a Mealy mission, the output produced by each transition depends on the internal state prior to the transition and the input symbol used in the transition. So we can think of the output produced during the transition. What does Moore mission do? In a Moore mission, every state is associated with an element of the output alphabet. Whenever the state is entered, this output symbol is printed. The output is produced only when a transition occurs. Thus, the symbol associated with the initial state is not printed at the start but may be produced if the state is entered at a later stage. Moore and Mealy missions are finite state missions. Of course, they are finite state missions with output capabilities. It is absolutely right. So, A is included. We'll go to the fourth point. Moore mission is not a finite state mission. This is actually contradicting the A statement. D is false. And both these options can be ruled out. Next, we will see about their equivalence. Moore and Mealy mission equivalence. If a problem can be solved by a mission of one type, it can also be solved by the other type. In this sense, the two types of transducers are possibly equivalent. So, B statement. Any given Moore mission has an equivalent Mealy mission is true. Any given Mealy mission has an equivalent Moore mission in C statement is also true. Option number 2, A, B and C only will be the right answer. Next question. Match list 1 with list 2 according to the input to the compiler phase that processes it. So let's see a diagram here. Usually we say lexical analysis is about token stream processing. We say syntax analyzer is about syntax tree processing. But here the input part is given in one side and the phase is given in the other side. Now whatever is given above the box is the input part. This is the input to lexical phase. This is the input to syntax phase. This is the input to semantic phase. This is the input to intermediate code generator phase. So we will go with the diagram order. Character stream is an input to lexical analyzer phase. So D will be mapping to 3. We have 3 options. Then we have token stream as the output from lexical analysis phase. So token stream becomes the input of syntax analyzer phase. So C will be mapping to 4. D3, C4. We will rule out the others. So after syntax analysis, we get a syntax tree here. This syntax tree in A will be an input to the semantic analyzer phase. So after semantic analyzer also we have a syntax tree here. But do we have intermediate code generator in the list 2 part? No, we don't have. We have only code generator part that is present here. So syntax tree will become an input to the semantic analyzer phase. So A will be mapping to 2. After that we have intermediate representation in B. So we have 2 intermediate representation here as input, 1 to mission independent code optimizer and 1 to code generator. So here the option is code generator. So we have to consider this part. So B will be mapping to 1. Option 2 will be the right answer. So we will also see another diagram. So this is the character stream and this is the token stream. This is the syntax tree. This is the intermediate representation and this is the target mission code. Next question. Arrange the following phases of a compiler as per their order of execution, start to end. We are starting with lexical analysis. So it starts with E. Then we have syntax analysis. It is B. Then we have semantic analysis. It is D. Then we have code optimization, which is C. So there are actually 2 phases of code optimization. One is for mission independent optimizer and another one is mission dependent optimizer. So after target code generation there is an optimization and before target code generation there is an optimization. So let's check the option EBD. It is given here and it goes with C next. So optimization is about mission independent optimization. So we will mark C. Then comes target code generation, option A. So EBD CA. Option number 3 will be the right answer. So regarding the other EDB. So it is saying E means lexical to semantic. So this order is totally wrong. And starting with syntax analysis is also wrong. With this we are completing Unit 8 solutions.